They just look like this, okay? Now we have an interpretation of actually what this represents. So they look like fractions. They have a numerator and they have a denominator. But what's important is this, is that the numerator and the denominator, the a and the b, can be any integer, okay? So they can be elements of z, okay? But the b cannot be equal to 0, okay? So this is a restriction. So actually, set builder notation, okay, the way it works is like this. We have what the things look like that are in the set, and then we have the constraint associated with the items that make up the elements, okay? So actually this is like a guard. This is like a bouncer over here. You're only allowed in here if the value of a and the value of b are integers, okay? Let's just keep in mind what they are, okay? So the integers are the value of a or b can be any one of these numbers, with one exception, that the b value cannot be 0. Okay, if that makes sense. And this is what we call the rational numbers. It's the set of all fractions. And actually, let's just keep in mind here is that when b is equal to 1, okay, well then this set here looks something like this. It's the set of a's over 1 such that the a and the b are elements of z, and the b is not equal to 0. I'm just throwing these constraints in. Actually, the b value we've chosen, it's 1. Okay, and the b value is 1 is not equal to 0, so we match that condition here. And now all we're left with is a over 1, which is just a, and a is an element of z. So actually this set here, when b is equal to 1, is the set of integers. So actually what we can see now is that the actual integers are contained within the rationals. Actually, more importantly, from a subset perspective, okay, from a subset perspective, yeah, we can actually see we can actually see a chain of relationships. Hopefully we can see that the natural numbers, symbolized by n, is a subset, okay? It's a subset. Is it a proper subset? Is it... This is going to be... We'll probably have to come back to this here, okay? It's a subset, okay? That's actually the same amount of numbers from a countability perspective, but we won't worry about it, okay? So the natural numbers is a subset of the natural numbers inclusive of 0. And they're a subset because they're all contained inside the integers, okay? They're all contained inside the integers, and the integers, as we just shown, are a subset of the rational numbers, okay? So there we go. Okay, now I have another video that actually shows that there actually is a set of numbers bigger than the rationals, okay? There is some numbers out there that we cannot represent as a fraction, okay? Some examples of numbers that cannot be represented, okay, as, let's say, rationals, okay, fractions, okay, are things like the square root of 2, okay. That's something that can't be represented as a rational. The number pi cannot be represented as a fraction. The number e cannot be represented as a fraction. The number square root of 2 pi cannot be represented as a fraction. There's so many of these, but I'll have proofs in relation to, well, probably not for pi and e in relation to that. These are irrational numbers, so we're probably a little bit advanced for what we're doing at the moment. Yeah, okay? Maybe actually we'll do a proof of that at some stage. Yeah, okay? But we can definitely do a proof that the square root of 2 is not rational, which actually creates another set of numbers which are known as the irrational numbers. Yeah, so the irrationals, okay, and we'll symbolize that by an I, okay, with, let's say, a small or for irrationals, and it's a set, okay, that contains numbers like the square root of 2, contains pi, it contains e, and actually it contains a lot of numbers. Yeah, okay, okay, and that's the irrationals. Now, the other set of numbers that we have, okay, so we're sort of getting there now, okay, nearly there, okay, is that if we take the rationals, okay, we're going to define what's known as the real numbers, the reals, okay. Well, the reals are symbolized by or, a bold or. Well, they're equal to the rationals unioned with this irrational set of numbers. Okay, so they're called the real numbers. And there's another set of numbers actually called the transcendental numbers, but we're not going to talk about that just here. Okay, and then finally we have this other, excuse me, we have this other set of numbers known as the complex numbers. The complex numbers, and we'll define the complex numbers with a C. Okay, and the complex numbers we'll define using set builder notation. It looks like this. It's an A plus bi such that A and B are elements of the real numbers, okay, and I is equal to the square root of -1. Okay, and you've probably seen them before. It's called the complex numbers. Okay, and I think that's probably where I'm going to stop now. Okay, so let's just run back through it. Okay, so what we have is we have the naturals, we have the integers, okay, we have the rationals, we have the irrationals, okay, we have the real numbers, the reals, okay, and we have the complex numbers. Okay. And there is other types of numbers in here called, you know, for example, transcendental numbers and so on and so forth. I'm sure there's many different types of numbers as well, yeah, that could be given a particular type of classification, yeah. Okay. But that's what we have, the naturals. So what I did say earlier on from a chaining perspective is that the naturals are contained inside the integers, okay, which are contained inside the rationals, okay. And I suppose we have Q unioned with the irrationals, okay, is actually equal to the set of real numbers, okay. And we also have then that the real numbers, well, when b is equal to 0, b is a real number, okay. Okay, 0 is a real number. When b is equal to 0, this set of complex numbers, it'll be a plus 0i, okay? Well, 0 times I is 0, actually reduces down to the reals. So we actually now have that the reals are also a subset of the complex numbers, okay? So this is sort of our chain that we have, yeah, in relation to the chaining of these number systems together. Okay, guys, once again, my name is Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland, and I hope this video was in some way intuitive, and more importantly, like all of our videos, I hope they were actually helpful for you, and once again, thanks for watching.